1. Breakthrough in optics, decoupling angle and wavelength with bilayer metagratings. 2. Revolutionary metagrating technology, the future of light control. 3. Revolutionizing optics, breaking light's oldest rule. 1. Breakthrough in optics, decoupling angle and wavelength with bilayer metagratings. What if we could finally break light's stubbornest rule? Scientists have just shattered a fundamental barrier in optics using an ingenious bilayer design. This breakthrough allows unprecedented independent control over two vital properties of light: its color, wavelength, and its direction, angle. For decades, these were frustratingly locked together in periodic optical systems. Imagine trying to adjust a spotlight's beam angle without accidentally changing its color. That's the challenge researchers faced due to a phenomenon called angle-wavelength locking. This inherent link, stemming from natural dispersion effects in repeating structures, forced wavelength and angle adjustments to shift together. The consequences? Real-world headaches, rainbow artifacts ruining augmented reality displays, color smearing that blurs wide-field images, muddled spectral data from photodetectors bogged down by angular interference, and severe limitations in designing efficient directional light sources. Most experts considered this locking unavoidable until now. But here's the revolutionary twist: a collaboration between Professor Jian-Wen Dong, Yat-sen University, and Professor Zhou, Fudan University, publishing in eLight, discovered that radiation directionality holds the key. Their theoretical work produced a complete phase diagram revealing two non-negotiable physical conditions: spatial inversion symmetry and highly directional radiation of optical modes. By introducing a precise lateral misalignment in bilayer metagratings, structures preserving inversion symmetry while breaking vertical mirror symmetry, they engineered radical control. Theoretically, this design forces resonant reflection only at a specific angle, normal incidence, and wavelength. Crucially, they devised general blueprints for achieving this pinpoint spatio-spectral selectivity at any desired angle and wavelength. Think of radiation directionality as a spectral eraser, the team explained. It lets us precisely suppress unwanted light signatures along a dispersion curve, decoupling angle and wavelength control, something intrinsic dispersion always prevented. This isn't just theory. Fabricating these bilayer metagratings demanded extreme precision, atomic-scale flatness for ultra-thin spacer layers, and near-perfect lateral alignment, 10 nm accuracy. The scientists pioneered a novel multi-step process combining advanced etching, indirect thickness measurements, iterative deposition, and a high-precision alignment technique. This birthed robust near-infrared devices. And here's the proof: experiments confirmed high reflectance occurring exclusively at a single angle and wavelength. Angle-resolved microscopy and cross-polarization measurements directly linked this to the predicted unidirectional radiation. Pushing further, they built millimeter-scale versions achieving stunning high-contrast imaging at 0 degrees and 1,342 nanometers, showcasing concurrent spatial and spectral selectivity. This leap enables compact optical imaging and computing previously deemed impossible. Controversially, this overturns a bedrock belief that angle-wavelength locking was an insurmountable fact of optics physics. Could this rewrite textbook principles? The implications are vast. Crystal-clear AR/VR displays free of rainbow glitches, razor-sharp spectral imaging, revolutionary coherent thermal sources, and breakthroughs in semiconductor manufacturing. Is this the start of a new era for photonics? What long-standing optical limitations might fall next? We'd love to hear your thoughts. Do you believe this can rapidly transform optical technology, or are there unseen hurdles? Share your perspective in the comments. Reference: Zhuang et al. Overcoming intrinsic dispersion locking for achieving spatio-spectral selectivity with misaligned bilayer metagratings. eLight, 2025. DOI 10.1186/S43593-025-00092. Y. Stay ahead of science's cutting edge. Subscribe to the SciTech Daily newsletter, https://scitechdaily.com/newsletter. 2. Revolutionary metagrating technology, the future of light control. Imagine a world where your augmented reality glasses could effortlessly filter out visual clutter, allowing only the light you want to reach your eyes, not just by color, but by direction. Sounds like science fiction? Well, it's closer to reality than you might think. A groundbreaking discovery by physicists in China has unlocked a new level of precision in light control, promising to revolutionize everything from AR/VR displays to quantum photonics. But here's where it gets controversial. Could this technology also reshape how we interact with the digital and physical worlds, blurring the lines between them in ways we're not yet prepared for? Let's dive in. In a study published in the journal eLight, researchers from Yat-sen University and Fudan University have unveiled a bilayer nanostructure, dubbed a metagrating, that can selectively filter light based on both its wavelength, color, and direction. This spatio-spectral selectivity is a game-changer, offering unprecedented control over light's behavior. Think of it as a super-precise bouncer for photons, letting only the right ones through the door. And this is the part most people miss. Traditional optical filters can either block specific colors or control the angle of light, but doing both simultaneously has been a long-standing challenge. It's like trying to isolate a single note from a specific instrument in a symphony, nearly impossible with conventional tools. The metagrating, however, achieves this by leveraging a phenomenon called photoresonance, which creates sharp peaks and dips in light reflection. By exploiting radiation asymmetry, the researchers broke the intrinsic locking between wavelength and angle, giving them independent control over both. Their device consists of 2 nanoscale silicon gratings stacked with a slight lateral offset and separated by a 35 nanometer spacer. This misalignment disrupts mirror symmetry while preserving p-symmetry, a crucial balance that enhances precision. In experiments, the team demonstrated that their metagrating could reflect light only when it hit at a 0-degree angle and a specific wavelength, 1349 nanometers. With a remarkably narrow bandwidth of plus or minus 5 degrees and 14 nanometers. In practical terms, this acts as an ultra-thin optical gatekeeper, ensuring only the right light passes through. To test its real-world applications, the researchers built a prototype and used it in an imaging experiment. When illuminated with a tunable laser, the metagrating selectively blocked or allowed light to pass, depending on its angle and wavelength. This resulted in an intensity contrast of 6.2 between on-resonant and off-resonant states, proving its effectiveness without bulky optics or moving parts. The implications are vast. In augmented reality, future headsets could use this technology to block stray reflections or enhance digital overlays, reducing eye strain and improving clarity. Because the devices are ultra-thin and passive, no power required, they could seamlessly integrate into everyday lenses, paving the way for a new era of AR. But here's a thought-provoking question. As AR becomes more immersive, will it enhance our reality or distract us from it? Let us know in the comments. Beyond AR, this technology could revolutionize thermal engineering by enabling directional thermal emitters, which radiate heat in specific directions and wavelengths, a boon for energy efficiency and stealth applications. It could also enhance laser systems by providing finer control over beam quality and emission. In biosensing and spectroscopy, the ability to precisely manipulate light at the nanoscale could lead to more accurate and sensitive tools. The researchers also provided a detailed phase diagram mapping how structural parameters affect the device's selectivity, offering a roadmap for future innovations. Our proposed phase diagram is general and can be extended into other spectral ranges with appropriate materials, they noted. This opens the door for tailored devices across various wavelengths and materials. In an era where light is central to communication, computation, and sensing, this technology could be as transformative as the invention of lenses or lasers. Whether it's making AR glasses smarter, lasers sharper, or sensors more precise, metagrating-based technology promises to sculpt light with atomic precision. But as we stand on the brink of this revolution, we must ask, are we ready for the ethical and societal implications of such power over light? Share your thoughts below. Tim McMillan, a retired law enforcement executive and investigative reporter, co-founded The Debrief. His work focuses on defense, national security, and psychology. Follow him on Twitter at LTTimMcMillan or reach out via email tim@thedebrief.org/lttimmcmillan@protonmail.com. 3. Revolutionizing optics, breaking light's oldest rule. Imagine a groundbreaking discovery that challenges the very foundations of optics as we know it. A recent study has unveiled a remarkable technique that defies light's long-standing principles, potentially revolutionizing the field of optics forever. Light possesses two essential characteristics: wavelength and propagation direction, or angle. The ability to manipulate both a specific wavelength and a specific angle is crucial for a variety of advanced optical applications. However, a significant challenge arises from the inherent dispersion found in periodic systems, which creates a binding relationship between angle and wavelength within the resonance spectrum. This means that altering the angle of incidence typically results in a corresponding shift in the filtering wavelength of optical devices. This angle-wavelength relationship complicates independent control and imposes significant constraints on optical applications. For instance, in augmented reality, AR, waveguides, dispersion can lead to rainbow artifacts, while wide-field imaging can suffer from image quality degradation due to lateral chromatic dispersion. Additionally, angular crosstalk in photodetectors can diminish the accuracy of spectral reconstruction, and there are inherent limitations in designing efficient directional light sources. In a groundbreaking paper published in eLight, a collaborative team of researchers, led by Professor Jian-Wen Dong from Yat-sen University and Zhou from Fudan University, has identified a crucial factor that could help overcome this fundamental obstacle: the directionality of optical mode radiation. Through comprehensive theoretical analysis, they developed a complete phase diagram that illustrates how to engineer resonant spectra by manipulating radiation directionality. Their findings indicate that maintaining spatial inversion symmetry and achieving highly directional radiation of optical modes are vital physical conditions for breaking the angle-wavelength locking phenomenon. Building on this insight, the researchers introduced a lateral displacement in bilayer metagratings. This innovative design maintains spatial inversion symmetry while disrupting vertical mirror symmetry, allowing for precise control over the directionality of radiation. Theoretically, they predicted that resonant reflection would occur exclusively at normal incidence and close to the central wavelength. They also proposed general designs that enable spatio-spectral selectivity at any angle and wavelength. As they aptly put it, radiation directionality acts like a magical eraser, enabling us to effectively suppress light's spectral signature along a dispersion curve. This capability allows for independent selectivity of angle and wavelength, thus overcoming the limitations imposed by intrinsic dispersion. However, the experimental fabrication of these bilayer metagratings presents its own set of challenges. Achieving the necessary flatness of ultra-thin spacer layers and ensuring precise lateral alignment between layers demands advanced nanofabrication techniques. To tackle this issue, the team devised a novel fabrication method that incorporates multiple etching steps, indirect thickness measurements, and iterative deposition processes. This approach, combined with a high-precision bilayer alignment technique, successfully produced high-quality bilayer metagratings that operate in the near-infrared spectrum. This method not only ensures excellent spacer flatness and thickness tunability, but also achieves alignment accuracy of approximately 10 nanometers, making it compatible with various spacer materials. This establishes a versatile experimental platform for exploring bilayer photonic systems. Utilizing this platform, the researchers demonstrated high reflectance occurring at a singular angle and wavelength. To validate that this novel reflectance stems from the radiation directionality, they conducted angle-resolved optical microscopy measurements to analyze the radiation directionality of the sample. By integrating temporal coupled mode theory with cross-polarization measurement techniques, they quantitatively assessed the unidirectional radiation of the resonant modes. Moreover, the research team has made significant strides in developing millimeter-scale, high-precision bilayer metagratings, achieving high-contrast imaging with simultaneous spatial and spectral frequency selectivity at 0 degrees and 1,342 nanometers. This advancement paves the way for new possibilities in compact optical imaging and optical computing technologies. In conclusion, this research not only presents an innovative solution to the long-standing challenge of independently controlling angle and wavelength, but also offers fresh perspectives for technological applications in areas such as AR/VR displays, spectral imaging, coherent thermal radiation, and advanced semiconductor manufacturing. What do you think about this breakthrough? Could it reshape the future of optical technologies? Share your thoughts in the comments.